Okay, let me just start by letting you guys know tomorrow there's not going to be an AGC seminar. But on Thursday we have the mathematics colloquium. The speaker is going to be Matt Baker from UC Berkeley. And his talk actually is kind of AGC related. Maybe on Thursday I'll say a little bit more about what the talk is about, but I encourage you to come. Okay. Okay. Now what I want to do today is the following. So last time we talked about, or in the last couple of classes, we talked about symmetric functions. So we define SYM to be the symmetric functions in an infinite number of commuting variables. Okay. Let me remind you that we had several bases for this space. We had the monomial symmetric functions. So remember what this was is something like n3 to 1 is going to be the sum of xi cubed, xj squared, xk over ij and k different from each other, right? So we basically said we put the monomial with exponents 3, 2, 1, and then since this is supposed to be symmetric, we look at all the other monomials that need to appear, and that's the monomial symmetric function. We also had the elementary symmetric functions. Okay, so remember how this goes. The elementary symmetric function of a partition is given by multiplying the elementary symmetric functions of the individual numbers. And each one of these, so E3 is the triple sums over ij and k different from each other. E2 is the double sums, sum of xj over I different from j. And E1 is just the sum of the variables. Okay. So this is also a basis for the symmetric functions. And a third basis that we studied is the basis of homogeneous symmetric functions, or rather complete homogeneous symmetric functions. Complete homogeneous symmetric functions. Okay, so for example, the complete homogeneous symmetric function h3 to 1 again is you multiply the ones of the individual numbers, and then each one of these things consists of like h3 consists of all the monomials of degree 3. Okay, so one way of writing this is in terms of the for example, we can write it in terms of the monomial ones. So h3 is all the different monomials that you can make of degree 3. So that's them. H2 is all the monomials of degree 2. And H1 is all the monomials of degree 1. Okay? And we saw that each one of these is a basis. And they're different for different, they're useful for different reasons. And it's useful to be comfortable going back and forth. Okay? And as I said, I'm only scratching the surface of this. It's well understood how to go from one basis to another one, what the transition matrices are, etc. Okay. And in particular, one thing that I want to point out is that there's at least two other bases that are very important. One is called the power sum symmetric functions, and the other one are called the Schur functions. And if you keep going to, if you end up working in combinatorics, or if you keep going to combinatorics seminars, you're going to see Schur functions appear all over the place. Schur functions are a very important basis of the symmetric functions that we're not going to talk about, but that are very, very important in representation theory and other areas. Okay, so let me actually just write it down, even though I'm not going to say much about it, just so that you see it written. So these are the Schur functions. Okay, and I'm sure you'll encounter these later on in life. Okay. So one thing we saw about this, though, is that actually, okay, so SYM is a Hopf algebra. And we saw that actually some of these bases are extremely useful if we want to abstract the Hopf algebra structure and not have to deal with manipulating the individual functions. So we saw that the algebra structure was given by the following. So we proved that as an algebra, the symmetric functions are precisely the polynomials in the EIs. Okay, so they're freely generated by E1, E2, etc. So every symmetric function can be written uniquely as some polynomial in the EIs. Okay, and we actually saw that this is also the case if we use the complete homogeneous symmetric functions. Okay? And so this determines the algebra structure completely. Now, one thing you should realize about this is that if we want, I mean, there's a very slight difference between this and what we normally call the ring of polynomials in these variables. And the difference is that actually we want this to be a graded algebra, right? And so the algebra structure is given by this. But what is the grading on this algebra? If you want to make this into a graded algebra, then you have to say what degree each element has. Okay? And what degree does the generator En have? N, right? Which is not the way it is in the usual polynomial ring. In the usual polynomial ring, everything has degree 1. Okay, but here it's a little bit different because E1 has degree 1, E2 has degree 2, etc. Okay. And similarly, Hi is homogeneous of degree n. Hn is homogeneous of degree n. Okay? But this is going to be important to get the grading right. Okay, now what about the coalgebra structure? Well, we computed the coproduct in either of these bases, and we saw that it is actually pretty simple. Delta of En is the sum from k equals 0 to n of ek tensor En minus k. Or if we wanted to do it in this other basis, then the formula looks exactly the same. Okay? And so this means that we can, and we talked about this, we can think of this as being kind of a Hopf algebra of sticks, where En represents a stick of length n, and the coproduct is breaking it in all possible ways as two sticks. Yeah? Yes, these are supposed to be h's. Thank you. Okay, so that is the co-algebra. So we have the algebra, we have the co-algebra, and then finally to have a Hopf algebra, we need the antipode, and we computed the antipode to be pretty simple. The antipode of En was just minus 1 to the n hn. Right? Or if you want it in the other basis, then S of hn is minus 1 to the n En. Okay? And so if we want to present SYM as a Hopf algebra, then one way of doing it is this. And then we can basically forget what these things represent. And we have this very nice, simple presentation of it as a Hopf algebra. Okay? So are we pretty happy with this? Okay. So what I want to do next, what I want to do today is talk about some variants of this Hopf algebra of symmetric functions. There's some variants, generalizations, extensions, and we're going to see a couple of them. Okay, so one thing that you might wonder is here, this whole structure is commutative in nature, right? I mean, you can see it in two ways. We said that the variables were commutative. And so this is one place where we instituted commutativity. And also here, we said that the EIs are commutative, right? And so this is the second place where commutativity arises. And so you could ask, okay, well, what if I want to do this without assuming commutativity? Okay. And this kind of goes with the principle that the more general your objects are, if you can go somewhere more general and prove things about that more general context, then you can try to push that down to more concrete contexts. Okay. And so you can think, okay, what about a non-commutative version of this? So let me ask you guys, how would you define a non-commutative version of this object? I'll take suggestions. Any kind of suggestion.
Start instead of with the commuting out variables, have them non-commuting, so like variable position.
So one thing I could do to look at this in a non-commutative context is just start with the same setup, except just get rid of this adjective of commuting indeterminates. Okay? Just take the xi's to be indeterminates, except that they don't have to commute with each other. Okay? So xi xj is not equal to xj xi. So I could define something called NSYM, and these are symmetric functions in non-commutative variables x1, x2, etc.
Could you just give two contrasting examples here so just like ones?
Yeah, so let's talk about how this is similar or different from SYM. So what does an element, can you tell me an element of NSYM that doesn't quite fit into SYM, into the context of SYM? What is a symmetric function in non-commuting variables that isn't exactly one of those guys? I mean, maybe one thing I should say is that those guys live into here, because, for example, I could. Okay, so maybe we can write an example. This thing, sum over I different from j different from k of xi cubed xj squared xk. Should we call this symmetric in non-commuting variables? Well, this is symmetric in the sense that if you relabel the variables, the summation just moves the variables around, and you're not going to change this expression. Okay, so this is symmetric. So how is this different from that? The only difference is that there things commute, here they don't. And so here we have to be a little bit more careful and remember that we're supposed to multiply xi, 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 then xj, xj, then xk. Okay? So what would be a different example of a symmetric function in non-commuting variables that maybe isn't quite that?
xi, xj, xi.
Something like sum over I different from j of xi, xj, xi. So again, this is symmetric in the sense that if you relabel the variables, then since you're summing over all different pairs I and j, this is going to be symmetric. Okay? But now this is, in this context, this is different from, so this is different from the sum over I different from j of xi squared xj. Yeah? And so that's basically the difference, that these two things, well, they both fit over there, but over there they're equal, and here they're different. Okay? Because over there we have the relation that we can commute them, but here we do not have that relation. Okay? So which one is bigger? Is this bigger or is that bigger? This one is bigger, right? Because for every one of these terms, I mean, for example, this function over here, this symmetric function commuting variables, corresponds to several over there, which are the different ways of grouping this multiplication. Here they're the same, there they're different. Okay? So this is going to be a bigger object.
Got a very type of question here. So suppose it has n variables in here. How much bigger is that? Infinitely bigger, or how much bigger? What is the direction?
So that's a great question. How much bigger? And by the way, before I continue, let me say number 1 here, because this is only one of the constructions we're going to consider. How much bigger is this? Or is it bigger? What do we mean by bigger? Like? Is it actually bigger? I mean, if we actually look at the card, well, first of all, these are vector spaces, so maybe we should compare their dimensions. Now, is the dimension of this really bigger than the dimension of that? Well, they're both infinite dimensional. So is it the same infinity? If you think about it for a little bit, you'll see that it is the same size. As you know, the infinite cardinality of this dimension is equal to the infinite cardinality of that dimension. Maybe that's not too hard to believe. But still, I would say that this one feels bigger than that one. So how can we actually say that this is bigger?
Can we form an injective
Just switch my battery for a second. Can I find an injective map from SYM to NC-SYM?
And then we show that's not a surjective.
And show that it's not surjective. Would that mean that it's bigger? I mean, I think we can, right? So what is a mapping from SYM to NC-SYM? Take the thing and put it in here, right? Is that a, what kind of function is that? Is it a linear function? Take the M3 to 1 and map it to this, and so on. Is that a linear function? Well, we can extend it linearly. Is it an algebra map? Does it respect multiplication? It's tricky, right? If you multiply, okay, so let me. So if you map M1 into here, it's just going to be the sum of the xi's. If you map M1 into here again, it's going to be the sum of the xi's again. What is M1 squared over there? So let's consider the function from SYM to NC-SYM. Okay, that takes a monomial m lambda and maps it to the same monomial function over here. Okay, so the question is whether this is an algebra map. So I'm saying why don't we compute f of m1 and figure out if that's equal to f of m1 f of m1. So what is f of m1? Well, f of m1, this is equal to the sum of xi squared, right? And we want to know whether this is equal to f of m1, which is just m1, and f of m1, which is just. Okay. So what do we get here? We get, this is f of the sum of xi squared plus 2 times the sum of xi xj. So m2 and m1. And what do we get here? We get the sum of xi squared plus the sum of xi xj plus the sum of xj xi. Are they the same thing? This gets mapped to sum of xi squared. This gets mapped to this. And do we get the same thing as here? No? This is summing over all I, this is summing over I different from j. This is summing over all I, this is summing over I different from j, I different from j. They actually are the same thing. So is that bad luck or? What if we do f of m2 n1? So we get sum of xi squared here. Here we get f of, what is this? Sum of xi squared and sum of xi. Okay. So on this side, we're going to get sum of xi cubed plus sum of xi squared xj plus, is that it? So this is going to appear like this. We get this. We agree? Are you checking me? So when I multiply sum of xi squared times sum of xi, I get the xi squared times xi, and I get the xi squared times the xj's. What about over here? Xi squared xi. So when I do that, I get the same thing. I get sum of xi squared xi, and so is it the same thing or not? It looks fine to me. It looks like it is the same thing, right? So what is the problem? The problem is that, okay, we're going from symmetric to, from commutative to non-commutative. But the thing is that we have the symmetric group permuting everything around, okay? And so even though individual things don't commute here, because we have the symmetric function permuting everything around, you have all the possible versions of the non-commuting thing, right? You have, you know that if you have xi squared xj, you have every single x something squared x something. Okay. Yeah?
What if this map not be well defined though? Because those two things at the bottom are two different things, but they're the same thing in symmetric functions. So the map would map the same thing with two different things.
So the question is whether this map is well defined, and I think it is well defined the way that I wrote it here. I'm starting with a basis here, and I'm deciding where to map it. And so I'm saying take the monomial symmetric function and map it somewhere, and extend linearly. And this is well defined. I think the issue though is that, and what you're pointing out is that I'm never going to hit this guy as an image of an individual m lambda. Okay. And in fact, you can see that this map is not surjective, which is what you were suggesting. Okay. So question, why is this map not surjective? Not surjective, why? Well, let me show you a different way of quantifying how these things are different. Okay, we deal with a lot of infinite dimensional things here in this class, but still they feel finite, and a concrete way in which they are finite is that for a finite degree, things are finite dimension. Okay? And so we can actually talk about what the degree is what the dimension is in degree n. Okay? So what is the dimension of the degree n polynomials in symmetric commuting variables? Well, remember that a basis for this is given by the partitions of n. We wrote it over there. So this is equal to the number of partitions of n. Okay, so it's called P of n. So now, what is the dimension of NSYM n? Well, to say that, I should figure out what a basis for NSYM is, which we don't really have yet. So let's think about what a basis is. So let me just make a claim. Well, let's talk about what are the possible monomial. What are the things like this? Okay, what should I call something like this? I would call this thing there are several different ways of indexing it, but one way in which I can index it is by calling it M sub 1, 3, 2. What does this mean? It means I have three variables. Sorry, I have degree 3, and the first and third term are equal, and the second term is some other term. Okay? So let's talk about another term. For example, what is m sub 1, 2, 5, 3, 6, 4? What does this represent? It means that I have a monomial of degree 6. So it has 1, 2, 3, 4, 5, and 6 terms. Okay. Where should I put x1? Or sorry, where should I put xi? I should put it in the first, second, and fifth coordinates. Then I should put a different variable in the third and sixth coordinates. And then I should put a different variable in the fourth coordinate. Okay? So do we agree that any monomial that you can write in non-commuting variables corresponds precisely to one of these things? So this is what's called a set partition. It's partitioning not the number 6, but into 3 plus 2 plus 1. I mean, if the variables were commutative, then this would just be xi cubed xj squared xk. Right? This is one of the terms of that n3 to 1. Okay? But here, I not only have to specify how many there are, but where they are with respect to each other. So what I have is not a partition of the number n into 3 numbers. What I have is a partition of the set n into 3 sets. So, in general, so a set partition of n is a way of writing n as a sum of, as a disjoint sum of sets. Okay? And then the claim is, and actually this is, okay, so the claim is that if I look at the monomials sub pi as pi range over all set partitions, then this is a basis for NSYM. This is one of these claims that in any proof they would probably just say, proof, obvious. And so think about it until you believe that, because it's one of these things where there's really not that much you can argue. It's not that you can make a logical argument, oh, this is why. Actually, you just kind of have to stare at it until you believe that. Basically, the point is that as soon as you have this monomial, then, because you need to permute, because this needs to be symmetric, if you have this particular monomial, x1, x1, x2, x3, x1, x2, by symmetry, you have to have all the ones for different values of ij and k. And so that means that if you have this monomial, you have this whole m sub pi. Okay? And so every symmetric function in non-commuting variables, you just look at the individual monomials it has, and because it has to be symmetric, that means that it has to contain the whole sum, and so it actually has to be a sum of these guys. And that's basically the proof. So it's a lot of hand-waving and not a lot of argument to make there. Okay? So what is the dimension of NSYM in degree n? This is going to be equal to the number of set partitions of n. And this has a name which I think is Bell numbers, but let me not write it down in case that's not true. Number of set partitions of n, the set of n elements. Okay. But so then for n equals, when do these become different? For example, for n equals 4, what are the partitions? You have 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So these are the partitions. What are the set partitions? I need to partition the set from 1 up to 4 into into these parts. So I can either put all the numbers together, or I can put 3 of them in one block and then the other one in a different block. So there's 4 of these guys. 1, 2, 3-4, 1, 2, 4-3, etc. Or I can partition them into blocks like this. How many of these are there? One has to be in a block with somebody. And as soon as you choose who the partner of one is, this is determined. So there's actually only 3 of these. What about these guys? Either one is in the pair block, in which case you have to choose its partner. There's 3 partners. Or one is in one of these blocks, in which case you have to choose its non-partner, and then the rest is determined. I'm doing this a little bit quickly, but basically that means that the dimension of SYM4 is 5, and the dimension of NC-SYM4 is 15. Okay? And that's a concrete way in which we know that this is bigger than this. And clearly, in general, it's true that this is smaller than this, because you can see that actually we're making a side-by-side list, where on the left side I have one number partition, which turns into several set partitions. So this is always bigger than this. Okay, this is a way of quantifying the observation that you guys made. Okay? So that's NC-SYM. Any questions about NC-SYM? I hope immediately a lot of questions start firing in your head, like, okay, are there other bases? Now, this is one basis, and this is the monomial basis. So can I find an elementary symmetric function basis? Can I find a complete homogeneous basis? What is the algebra structure? What is the co-algebra structure? What is the antipode? And these are all natural questions, which have been answered. And if you're interested in reading more about this, I recommend a paper by Mercedes Rosas and Bruce Sagan. But there's another one by, let's see, Bergeron, Rosas, Zabrocki, and I'm missing one author, and I forget who they are. But in these papers, they explore, in the Rosas-Sagan paper, they explore the algebra structure, and they explain it well. And then here they explore the Hopf algebra structure. Okay. So this is one way of considering a non-commutative version of symmetric functions. Okay. And naturally, I would say much more if we had more classes left, but I wanted to at least show it to you. Okay. Now, what would be a different way of finding a non-commutative generalization of this Hopf algebra? I mentioned that in symmetric functions, in our original symmetric functions, there were 2 places here where commutativity comes in. So one is when we're saying that the indeterminates are commutative, and a different place is when we say that SYM is generated by these guys freely commutatively. So E1, E2, etc. are generators, and the only restriction we put is that they commute with each other. Okay. And so the other thing that you could try to do is say, well, what happens if I consider this, except that I don't want these guys to commute anymore? And that's a second non-commutative version of this, which is also very interesting. So I'm still answering that question, what about a non-commutative version of this? I can do this in a different direction by defining a different Hopf algebra, which is usually called NSYM. And let me give you the reference for this. And again, here I'm sorry that I'm not going to remember all the authors, but I know Gelfand is one of the authors. Retakh is another one. Thibon is another one. And there's 3 more, and I'm forgetting who they are right now. So what is NSYM? Well, NSYM is just defined to be like this, except without demanding commutativity. Okay? So we just say that NSYM is by definition, okay, let me write it like this. By definition, this is K of E1, E2, etc., where the degree of En is also n. But these angle brackets mean that this is just freely generated by these guys with no commutativity between them. Okay. So this means freely generated. So non-commutatively. Okay. And so maybe before we continue, we should talk about what something like this. What is an element of this Hopf algebra? Well, so far I'm just defining an algebra. I haven't defined a coproduct. So what does an element of this thing look like? Well, by definition, it's just some kind of expression in the EIs, right? So something like E3, E1, E2, or let's say E3, E2, E2 plus E1, E2, E4, E1. And maybe you can put coefficients on it. Okay. So the elements of this are just linear combinations of words in the EIs. But again, the point is that E3, E2, E2 is different from like E2, E3, E2. Okay. Which is not the case in the original symmetric functions. How do I multiply? So what is the product? For example, how do I multiply E3, E2 plus E1 times E3, E1? Well, again, the point is that this is just multiplication is free commutative in the EIs, and so in this basis, all you do is you just linearly expand this out. And so you get E3, E2, E3, E1 plus E1, E3, E1. Okay? So this is what it means to be, for the algebra to be free. Just kind of multiply formally and you don't have any relations between things. Okay? So do you guys feel pretty happy if I give you 2 things in this algebra, you can multiply them? Yeah. Okay. So, yeah? I'm sorry?
Even for this case, y is not E2 squared. I understand that E3, E2 is not the same as E3, but why E2 is not the same as E2 squared?
I could write this E2 squared.
Oh,
yeah.
Okay.
I just wrote it like this, but I could write E2 squared.
Okay, sure.
So product is free in the EIs. And now coproduct. I actually just define it to be given by the same formula.
Do this because delta's a algebra.
So, right. So the thing is that why is this a proper definition? Because these EIs are free generators for the algebra, and so if I want to define the coproduct, I can just define it however I want on the generators because there's no relation between them. And then using this, I get, for example, the delta of E3, E2, E2 is just delta of E3 times delta of E2 times delta of E2, because the coproduct is supposed to be an algebra map. So that's my coproduct. By the way, you've seen this before, and this was your homework problem. Homework 4, problem number 2, I think. Part B was to find the antipode of this thing. And I actually even called it the non-symmetric, the non-commutative symmetric functions. That's what that problem was called. And I asked you to find the antipode. And you did it using the Takeuchi formula, and you got something, okay? But again, so it's a sum of -1 to the n times a big sum. It was this ugly expression. But again, the point is that if I introduce a new basis, then this is just going to be -1 to the n hn. Okay, but I have to introduce hn. So what is hn? So I define hn by saying that the sum of -1 to the k ek hn minus k is one if n is equal to 0, and 0 if n is bigger than 0. So you see, this is exactly the same equation that we had last time between the e's and the h's. Okay, and last time it meant something more. It meant that this was the elementary symmetric functions in commuting variables, and these were the complete homogeneous symmetric functions. Okay. Here I'm saying something different. I'm saying e's are just these symbols, and I'm saying that the symbol en just represents a variable that has degree n. And now I'm coming up with a new set of symbols h given by these equations. And actually what I'm giving you here is a recursive definition of the h's. Because, for example, if you want to, let's say that you already found h0, h1 up to hn minus 1. I claim that you can find hn using this formula. Why is that? Because if you look at the term k equals 0 here, the term k equals 0 is -1 to the 0. E0, which is 1. I didn't say that, but E0 is always 1. E0 is 1, and hn is hn. And so what you get here is hn plus a bunch of other things is equal to either 1 or 0. And so that gives you the definition of hn. Okay? And so I claim that if you define hn by this equation, then the antipode just works in the same way as it did here. Okay. So now let me ask you, again, is this bigger or smaller than SYM? Or incomparable? How did you think about that while I erase here? What do you think? Bigger. Why is it bigger? One reason is kind of the same thing as before, that things that commuted now don't commute, and so things that were equal now are not equal. And an example is staring at you right here. These two things in SYM, they're the same thing, but in NSYM, they're not the same thing. And so that gives you an indication that maybe this is bigger. To quantify this again, let's figure out what a basis is for this space. Okay? So what is a basis for NSYM? Well, we know that NSYM, by this definition, the elements of NSYM are just linear combinations of things like this. And that means that these words are a basis for NSYM. Now, how should we index them? So a basis for NSYM. Maybe let's think about something a little bit smaller. What about a basis for NSYM sub 3? What are the different things of degree 3 that you can have? So one example is E3. Now remember, it's very important to remember that EI has degree I. So E3 has degree 3. So what other thing is of degree 3? Okay, so what Brian was saying is that I should just look at all the ways of writing things where the subscripts are up to 3. E2, E1 is an example of something of degree 3. E1, E2 is something of degree 3. And E1, E1 is something of degree 3. Okay. So what is the basis for NSYM? A basis for NSYM is just the things of the form E sub C, which is equal to EC1, EC2, etc., where C equal C1, C2, etc., is what's called a composition. Okay. What are these CIs? They're just any numbers, but they have to be greater than or equal to 1. So what is the dimension of NSYM n? Is going to be the number of compositions of n. So the number of ways of writing n as a sum of other numbers. What's the difference between that and partitions? That partitions always have to be written in decreasing order, whereas compositions can be written in any order. So for example, okay, so this was SYM. SYM. This one is NCSYM. So we said this 1, 4, 3, 6, and 1. And now let's do this for NSYM. So how many partitions of 4 are there? You have 4. You have 3 plus 1, but you also have 1 plus 3. So we get 1 here. 3 plus 1 and 1 plus 3 give me 2 different partitions. 2 plus 2 is just 1 partition. 2 plus 1, I can reorganize it in 3 different ways. and 1 plus 1 plus 1, I can only reorganize that in one way. So the total here is 8. We said the total here was 15, and the total here was 5. Okay? So here's an easy lemma. The dimension of NSYM N is how much? In other words, how many compositions of N are there? Well, it turns out that there's exactly 2 to the n minus 1 of them. And the proof is that I have a bijection from the compositions of N to the subsets of the numbers from 1 up to n minus 1. What does this bijection do? It takes something like 1, 2, 4, 1. That's a composition of 8. And it sends it to the partial sums. Okay. So maybe let me write down the definition and then the example. So the example is this one, and I'm going to map it to the partial sums. So 1 plus 2 is 3, 1 plus 2 plus 4 is 7, and I don't bother writing the last one because it's always going to be 8. Okay, so if I have a composition C1, C2, up to CK, I map it to C1, C1 plus C2, etc., up to C1 plus C2, CK minus 1, the partial sums. The point is that if I cover up the composition and I only show you this, then you can tell me what the composition is, right? Because you just have to see what the gaps are. 1, and then between 1 and 3 there's 2. Between 3 and 7 there's 4, and between 7 and n there's 1. Okay? So this is a bijection between compositions of n and subsets of n minus 1, of which there are 2 to the n minus 1. Okay? Okay. So this one is easy, 2 to the n minus 1. These ones don't have such nice formulas. Okay. So this is NSYM. It's just defined formally in this way. And I give you the product, I give you the coproduct, and I give you the antipode. Okay. And it's another different non-commutative version of SYM. Okay. So do you guys have any questions about NSYM now? You happy with it? Yeah. That's right. There's no excise here. We just define it formally as, and maybe in the back of your mind you can kind of think that the e's are kind of like elementary symmetric functions, but I'm not saying that ek represents the following thing, in determinants x1, x2, etc. And that's kind of the point. The point is that in symmetric functions we have this great coincidence that the Hopf algebra symmetric functions is equal to this beautiful SYM that is represented very nicely by these EIs. And when you drop commutativity, this is not true anymore. And so we end up with 2 different definitions, and they're different from each other. So if you go the indeterminates way, then you end up with NC-SYM. And if you go with the generators and relations way, then you end up with NSYM. And they just end up being different from each other. N is kind of like non-commutative. And actually it's kind of confusing. NC-SYM is called the symmetric functions and non-commuting variables. NSYM is called non-commutative symmetric functions. you're going to confuse it each time, and just make sure to remember that there's two. And I actually have to confess that I prepared this class, and then I realized that I had confused the two, and I had to prepare it again. So just make sure that you remember there's two of them, and they're different from each other. Okay, so that's NSYM. So basis is EC over the compositions. Okay. So these are two different extensions of symmetric functions where we want to go towards non-commuting. Okay. So now what I want to do is discuss a third extension of SYM. A third variant and this third variant, so it doesn't have to do with non-commutativity anymore. What we're going to do is that we're going to consider functions in variables that are commuting, and we're not going to demand them to be symmetric. We're going to demand a little bit less of them. Okay. And so we're going to discuss quasi-symmetric functions. Okay, and let me say that for the rest of the few classes that we have left, this is going to be a very central object, more important than the two that I just talked about. So quasi-symmetric functions. Here, my setup is going to be again to start with indeterminates. So I start with x1, x2, etc., and these are commuting variables. I'm going to say that if I look at some function in these variables, okay, so something like sum of c alpha x to the alpha, okay. So some function in these variables, we're going to say that this is quasi-symmetric if whenever I look at this and this, so these are two different monomials that have the same exponents alpha 1 up to alpha k. Okay? And so in symmetric functions, whenever you have the same exponents, you have to have the same coefficient, right? So, for example, the coefficient of x squared y has to be equal to the coefficient of w squared z, or of a squared b, or d squared a. Anything squared anything always has to give you the same coefficient in symmetric functions. Here, I'm going to say that these have to have the same coefficient if these variables have the same order. So have the same coefficient whenever I1 is less than etc. less than IK, and J1 is less than ... is less than JK. And I think this is going to be clearest in an example. Let me try to do this example, and maybe this will answer your question. And if not, then I'll ask you again. So for example, let's say that I want to write down a quasi-symmetric function. And this quasi-symmetric function includes the term x2 squared x4. So what other terms do I have to put here? x1 squared x2, or x1 squared x3, or x1 squared x4, or x2 squared x7, or x8 squared x100, etc. Now, what is the difference with symmetric functions?
Do we have x2 squared x3 here? I'm just very curious.
We have x2 squared x3.
So you are just fixing that. No.
We have x100 squared x million. What do I not have to have here? What I don't have to have is x2 squared x1. Because what I do have to have is things where the first term is less than the second one. But I don't have to have x1, x2 squared. That's a different monomial in this quasi-symmetric context. Okay. So this is, in other words, what I'm writing here is the sum over I less than j of xi squared xj. Okay. This is something that is quasi-symmetric, but it is not symmetric, because this doesn't. If you swap the variables 1 and 2, then the function changes.
Yeah, but what happened to those like x2 squared x1? What happened to those monomials? Nothing.
Those don't have to be here. So, by the way, we should give a name to this. So, what should we call this? Well, this should be called a monomial symmetric function, presumably. Let me use a different letter. And how would you index this one? 2, 1. Now you're asking me where x1 squared x2 went.
No, divide by x2.
Sorry, x1 x2 squared. So where does x1 x2 squared belong? In what monomial function? This is a different monomial function called m12. It's the sum of xi xj squared, where I is less than j. Yep. Okay. So what am I doing here? I can define a basis. So what is a basis for QSYM? Well, the point is that you just choose exponents and you don't get to swap them. Okay, so the order is important. 2, 1 is different from 1, 2, and these are precisely compositions. So a basis for QSYM is this. Okay, and therefore QSYM also has this dimension. Okay. Yep.
Is SIM a quotient algebra of all these Hopf algebras that you've been running in the book?
It's a great question. Is SIM a quotient algebra? Let me delay the answer, but I will answer it. Okay. A very good question you should be asking is, how are these algebras related to each other? And that's where we're headed. So I will address that. Okay. Okay. So this is a basis for QSYM, and so I can add this to my table here. I mean, I think right now there's a question that you should be asking yourselves. Which is, if you have two algebras and they have the same size, you have to ask, okay, are they the same one? Maybe, maybe not. Okay. It turns out the answer is no. They're not the same one. Okay. So we define the objects. We define that it's a vector space. We know, I mean, it's clear how you should multiply these things. You just multiply as polynomials in the xi's. Okay? So if you want a Hopf algebra, then you need to define algebra. Okay, so how do you multiply? MC times MD. Well, the thing is that MC is just something. I mean, it's a quasisymmetric function in the xi's. And MD is also a quasisymmetric function in the xi's, and you just multiply that out in the xi's. Okay? And because this is a basis, you're going to get some. You're going to get something. Okay? So let me just say that the algebra is just given by manipulations in the xi's. Okay? But in particular, I'm not claiming right now that I have a free generating set or anything like that. I'll say something about that in a second. But let's talk about the coproduct. So what should we define the coproduct to be? So that's the algebra. Now if I want the coalgebra, then I need a coproduct. And so I need to decide what is the coproduct of a quasisymmetric function of x. Okay? Now, we already knew how to do this in symmetric functions. Remember, what we did is that we just took this and plugged in two sets of variables. And so we can do the same thing here. So just as we did earlier, and let me give you an exercise, and one that I really encourage you to do. Check that delta of M alpha is simply, I mean, this is a general definition of the coproduct, but I can also define it in terms of my basis, and it turns out that you get a nice answer. You just get the sum. So alpha is a composition. And what you get is simply the sum over all ways of cutting your composition into two. And then you get M beta tensor M gamma. Very easy. So for example, what is delta of M21? It's all the ways of splitting up the composition to 1. So it can be M21 tensor M empty, M2 tensor M1, or M empty tensor M21. Okay. So you might prefer this definition. This definition is more explicit than this, but it's good to know that it matches what we've done before. Okay. The antipode is also very nice. It's like I'm doing this in Arabic, going from right to left. Antipode is given by the following. If you want the antipode of M beta, you have to do minus 1 to the k times sum over, I'll parse this in a second. So I think this is clearest in an example. So let's say that I want to do S of the monomial quasisymmetric function M421. Okay? So what I do is that I reverse, first of all, I put a sign minus 1 to the k, where k is the sum of the numbers. of 7. Then I reverse beta. So instead of 4, 2, 1, I write 1, 2, 4. And then I look at all the compositions that refine it. Sorry, that coarsen it. So what I mean by that is you get to merge parts of the composition. So what are the ways of merging parts here? Well, I could merge 1 and 2. Or I could merge 2 and 4. Or I could merge all of them into 1. Okay. So you take your compositions and then you allow yourself to merge consecutive parts in all the possible ways. Okay. So this is the coproduct. This is the antipode. And so this gives you the full description of QSYM. Okay. Algebra, coproduct, and antipode. And let me conclude just by stating a theorem. If you have two algebras of the same size and they're not the same, then if you have two half algebras of the same size and they're not the same, maybe the next hope is that they're duals of each other. And it turns out that that's what it is. So QSYM